Dear friends, hearty welcome to the online problem solving session series organized by Maths Aspirants. As you may know, Maths Aspirants is a collective of math lovers across India, started by myself in 2017, and we used to organize several online programs to help the students. As a part of the online problem solving session series, today we are blessed to have Dr. Anand Oa with us to handle a session on sequences of real numbers. Dr. Anand did his graduation from UC College Alua, and then he cleared JAM examination with All India rank 9 and joined IIT Bombay for MSc. After that, he joined for PhD at IIT Madras and recently successfully defended the thesis and awarded PhD from IIT Madras. So it is my pleasure and privilege to introduce Anand to all of you. He is really an active member of our group from his college days itself. And I am sure that today's session will be really beneficial to all of you. So I request every participants to actively involve in the class and discussion and stay until stay throughout the session, and you can share your questions and comments, and also you can discuss that with Anand. So once again, I would like to express my sincere gratitude to Dr. Anand, and once again, I welcome everyone to this event. Welcome, Anand.
Okay, thank you. Good. So, good evening, everyone. So, thank you so much for your kind introduction, sir. So, thank you again for giving me this opportunity again. So, today I will talk. I'm planning to solve some problems on sequences of real numbers. So, mainly focused on IIT JAM examination. So we will be solving few of them. So I just want to make a comment that in between, if you are having a doubt or some comments, if you want to make, feel free to make those. So with that, I'll begin. I'll share the screen. Yeah. So as I said, we'll be discussing some problems from previous year IIT JAM exam, and also I have collected few more problems from other exams like TIFR and ISI. So yeah, let's begin. I will talk about the concepts which required to solve while we solve each problem. So we will go in that way. So maybe let us start with few problems on finding limits of certain sequences, certain type of sequences. So let's begin with the first one. So as you can see, what is given. So find the value of the following limit. So which is given as a product k equal to 1 to n, k by k plus n, whole to the power 1 by n. So they have given 4 options. So anyone has any idea how can we possibly approach this? Even if you don't know exactly, but you can give some ideas if you have. Maybe I'll wait for a few seconds.
So by using n-through test somewhere.
By n-through test, what do you mean? Like, can you elaborate on that?
Like I thought like 1 by n is being written there. So
yeah.
if I apply through test, then 1 by n will be not there. Then we can simplify the terms and applying limit will work out, I think.
Which test are you referring to? Is it about the series or so there is a root test for convergence, testing the convergence of series, and so which one did you mean?
So series, series.
So, but that is for testing convergence. Here we want to find the limit of the sequence. So that's the question is to find limit of this given sequence. So if you apply that, we can only talk about convergence of the series. So, did you get my point? Yeah, of course,
Yes.
that is right. It's in the nth root form, but the question is to find the limit of that sequence, not about the convergence of the corresponding series.
Okay, so I thought if we apply, like the value which are being shown there kind of shows it is convergence, but I thought if we apply that, then at the end we will get some values which will be related at it.
Yeah, probably, yeah, that won't be a good idea. But any other idea? Because so first of all, this is a product, right? So suppose if I can expand it, this is, let me write here. Just a second. Yeah. So 1 plus n to the 1 by n. Okay, maybe you can write this way. All to the 1 by n. So this is the sequence which is given. We want to find the limit. So it's a product form and there is a power in it. So usually, okay, let me call this sequence to be an. Now we want to find the limit of an. So usually when you have a product or you have a power sequences of that form, it is one idea is to take logarithm, right? So if you take log of an, what you get is 1 by n. Now you have to take log of the product, and which we know that it is log of the sum of the log of individual terms, right? So we can write it as log plus log now yeah, you can also write it in this way as well, like in the summation way. I just simply expanded it, but you can put it in this way as well. But this has a specific form, right? So some 1 by n summation k equal to 1 to n log k by k plus n if you are getting some idea in any of the step, you can unmute and tell. Okay. So this, what one can do is just take the n from the common from the both numerator and denominator. What you get, you can write it as k by n divided by k by n plus 1, right? And now can you identify? Okay, so I forgot to write log. So log a by n so now, so this is of this the following form, right? 1 by n summation k equal to 1 to n some f of k by n, where what is f? I write on the left, f of x is log x divided by x plus 1. Is it correct? So we wrote the sequence in the following way: 1 by n summation f of k by n. Now basically we want to find the limit of this. So can you identify this with some familiar limit, or do you know any, how you are you familiar with any similar form? So this you can view as So for example, if sorry, my drawing is bad. So if I can, I will roughly draw a figure of the graph of f. Let's say this is the graph. Then what exactly is this sum which we have written? So it is nothing but you just partition the space with the length of 1 by n. So n minus 1 by n. Then n by n, which is 1. Can you identify it as something? So I want f of 1 by n, then f of 2 by n up to so I'm just basically drawing those rectangles where the values are f of 1 by n, f of 2 by n, and so on up to f of n by n. So that is precisely the terms involved in the sum. Also, you have multiplied with 1 by n. So what this is basically the area of the sum of the areas of the triangles here, right? So what is this actually?
The Riemann sum under the tax partition approach.
Yes, so this is a Riemann sum, right, associated with the function f on that interval. From interval 0 to 1. So what is the limit of this Riemann sum?
Integral 0 to 1 fx dx.
Right? So that's the point. So I just want to make that concept clear. So this, we know that because the Riemann sum converges to the Riemann integral. So this converges to the Riemann integral of the function on the interval 0 to 1. So essentially what you need to find is just integral 0 to 1 f of x dx. That is the limit which we are looking for. Limit of log n. We want limit of n. So we took log, we wrote it in the following form. We identified that this is the Riemann sum of a particular function, and we know that limit of the Riemann sum is the Riemann integral. So what you need to do is just integrate. So in this case, what is f? F is log x by x plus 1. So that is what log, you can write as log x minus log x plus 1, right? So just integrate it. Maybe I can add a page. So what you need is, so what we figured out is limit of log n is nothing but integral 0 to 1 log x minus log x plus 1 dx. Is it clear till now?
Yes.
So now the only job left is to integrate this, which you know, right? How do we integrate log x? Or do you know the integral of log x?
By parts.
1 by
Yeah, so integral. So you can do it by parts, right? Integration by parts by taking 1, you see it as 1 into log x. Then use the parts, integration by parts, and you will get x log x minus x. That is the integral of log. That you just need to compute. Similarly, for log x plus 1, you will get just x plus 1 log x plus 1 then just apply the values 0 to 1. Just let me know if you are not clear with any of the steps.
Sir,
Huh.
there was one 1 by n in the summation of in the
Yeah.
common we took, sir. Right, sir? What do we do with it?
So so that is precisely the area, right? So what is the area of, for example, the first triangle? First rectangle. Its length is f of 1 by n. Its width is 1 by n. So 1 by n times f of 1 by n is the area of the rectangle. We have to take both together. Is that clear?
Yeah, okay, sir. Okay, sir, got it.
Yeah. So everything is considered. Nothing is left off. So yeah. So yeah, I probably don't need to do this. I think you can do it very well. So what you need, but still, just to complete the answer, I will just write. So minus 1 minus 2 log 2. Just let me know if I am making some mistake. Plus 1. The rest of them is 0. So basically what you get is minus of 2 log 2. So minus 2 log 2 is log what? Log 2 to the power minus 2, right? That is log 1 by 4. So what you got is limit of log an is log 1 by 4. Now how do you get limit of an? Just take the exponential of it. So just limit to n becomes exponential of log 1 by 4, which is 1 by 4. Now the reasoning is exponential function is continuous. That's why we are able to do it. So log n goes to log 1 by 4. So an goes to 1 by 4. So the answer is 1 by 4. Is it clear? If this is fine, then we will go to the next one. Okay, so I assume it is clear. So let's see another limit evaluation problem. So you're given a sequence. What is this? 1 by n cube plus 1 plus 2 square by n cube plus 2 plus up to n square by n cube plus n. So there is a particular pattern in the terms. You are supposed to find the limit of the sequence. Find the so then the sequence converges to what value? That's the question. So again, so you have 1 by n cube plus 1. 1 means 1 square. So 2 square by n cube plus 2. N square by n cube plus n. So any idea? So it can be wrong. But, yeah. What did you say? I did not hear you properly. Can you repeat?
Plus induced theorem.
You said sandwich theorem?
Yes, sir.
Okay. So how do one do that? Like how? So should I find something on the left and the right? What? So what should be upper bound and lower bound for this sequence, where both the left hand side sequence and the right hand side sequence converges to the same value? That's what you mean, right?
Yes, sir.
So can you tell me what can we take on the right hand side or the left hand side? Oh yeah, so yeah, all others can also think about it, like what method can be possibly used here. So
The left hand side is 1 by n cube plus 1.
1 by just n 1 by n cube plus 1.
1 by, yeah.
Okay.
RHS is n square by n cube plus n. That last one. Is it?
Just n square by n cube plus 1. But then so RHS should be bigger.
n into n square plus n into n square by n cube plus n. Is it, sir?
N into n square by n cube plus n. So so we need to be very clear about why that is the case. And even if that is the case, did we solve the problem using the sandwich theorem? Because the left hand side, which you said is converging to 0, the right hand side is n cube by n cube plus n, which converges to 1. So that's not giving us the final answer, even if that's the case. Yeah, everyone can think about it, can give ideas, it can be wrong, and yeah, if there is something wrong, we can discuss that. That makes more concepts more clear.
Sir, we can take the left side as summation k square by n cube plus n and the right side as summation k square by n cube plus 1. Then both the limit converges to 1 by 6.
So let me write what you said. Okay, so left hand side you said is summation. You said
K.
n cube.
K square by n cube plus n, where k varies from 1 to n.
K square by n cube plus n. Okay. And the right side is
Summation k square by n cube plus 1.
K square by n cube plus 1. Yeah. So this one, what you basically did is, for the right hand side, you kept the numerator the same, and the denominator you kept this n cube plus 1, right? So that it is bigger than the given sequence, given sequence, right? What others is it clear to others? So the first term you kept it as it is. Second term, denominator we replace by n cube plus 1 itself, so that it's a smaller numbers in the denominator. So this one is bigger. We did the same for each terms. Is that clear to everyone? Similarly, for the left hand side, to find the smaller number, you keep the denominator of n cube plus n throughout the terms, n terms. We did not change anything else, numerator. So is it clear that this one is less than or equal to this one, and this one is greater than or equal to this one?
Sir, can you explain it again, please?
Yeah, sure. So maybe I will not write in the summation form. Maybe I'll put it just to make it clear. I will write it as individual sums. So what we did is just this 1 square by n cube plus n plus 2 square by n cube plus n. And on the right side, what we did is 1 square by n, instead of everywhere n cube plus 1 in the denominator. 2 square, then n square by. So you see this, right? Numerator is the, so if you take individual terms, this is less than or equal to this, right? The first term, because the denominator is bigger compared to the denominator here. Numerator is the same. So this is less than or equal to this. Look at the second term. This is less than or equal to this, right? Similar to up to n terms. The same goes for the right hand side. This is less than or equal to this. The second one is less than or equal to this. The last one is less than or equal to this. Is it clear now?
Yes, sir.
Yeah. So that's the idea. Now what we can do now, since we have a common denominator, right? Now we want to expand expand left hand side, and we can expand left hand side and right hand side, right? So what can anyone tell me what it will be? What will be equal to and what this will be equal to? So we have a common denominator. So which is n. If you look at the left hand side, we have a common denominator which is n cube plus n. So we just need to add the numerator, right? Add up the numerator, which is 1 square plus 2 square plus up to n square. So what is that sum? Do you recall the formula? The sum of squares up to the n terms?
n into n plus 1 into n plus 1 by 6.
Yeah. By 6. Whole divided by n cube plus n is there, right? So we put n cube plus n. So this is less than or equal to, this is an, our an. And the last term is again n into n plus 1 into 2n plus 1 by 6 times n cube plus 1. Is it clear now? Now, what will be the limit of the left hand side and right hand side if you look at it? How can one find it? Where does this converge to?
1 by 3.
Yeah, so what the idea you used? How did you say that?
That took the common terms from numerator and denominator and
Exactly.
eliminated them.
Exactly. So if you look at these terms, this is a cubic polynomial by a cubic polynomial. Same goes for the right hand side, right? So what you do? In fact, the answer always going to be the quotient of the leading coefficients of the numerator and denominator. So what you do is you take n from the n cube from the numerator, n from each of the terms. So you take n cube out, then what you get is 1 plus 1 by n times 2 plus 1 by n. Now divided by 6 into, so here also n cube will come out. So that get cancelled. 6 into 1 plus 1 by n square. Less than or equal to an, less than or equal to, here also the same. N cube will come out. Then 1 plus 1 by n. 2 plus 1 by n cube. Yeah, so yeah, sorry, n cube. Is it clear? Any doubt? Just we took n cube from numerator and denominator. That's all. So in the numerator there were 3 terms. Just take n from each of the terms. So now can you find the limit? Because if you look at this thing, this converges, you know, 1 by n converges to 0. So this converges to 1. This converges to 2 plus 0, that is 2. This is 6 times 1 plus 0. So this converges to 1 into 2 by 6 into 1. That is 1 by 3. The same here also, it is 1 by 3. So by Q's theorem, we said that the middle sequence, which is the sequence which we are considering, converges to 1 by 3 because the left hand side sequence and the right hand side sequence both converges to 1 by 3. So an also converges to 1 by 3. So the 1 by 3 is the right answer. Is it clear? Okay. Yeah, you can feel free to ask if you have any doubt, even if it is very small. Okay. So this one, I would say it is a similar question. If only thing is that there is square root involved, that's the only difference. So let's say yeah, if anyone has any idea, just
So similar way we will do like squeeze theorem. So
okay.
left hand side will be n square plus 1 upon root of n raised to 6 plus n.
Okay.
And right hand side n square plus n upon root of n raised to 6 plus 1.
Okay. Okay. Fine. Let's see. So left hand side is this. So yeah, so you're saying the same, basically the same idea. Is this what you mean?
Yes, sir.
Yeah, so yeah, so that's the basic idea. Now how do we now what is the next step? Like you have to add them, right? So what is this and what is this? So you have a root of n power 6 plus 1 common, and you have to add n square plus 1, n square plus 2 up to n square plus n. So what will you get? So n square is repeating n number of times, right? So you get a n cube from that, plus then 1 plus 2 plus etc. up to n. So that you will get n into n plus 1 by 2. Is it clear? Same goes for here, n cube. Plus, if it's not clear, just let me know. We are basically adding all the numbers in the numerator, that's all. So n square is repeating n number of times, so therefore the n cube is coming. And then there is 1 plus 2 plus etc. plus n remaining, which is n into n plus 1 by 2. Now again the same story, like here it is a cubic polynomial in the numerator. Denominator, it's not a polynomial, but still the degree of the term, it is n power 6 inside the root. So altogether the degree is 3. So numerator and denominator has degree 3. So you again how to find the limit? Just take n cube out. 1 plus divided by 2n divided by root of. So what you get is this converges to 1 plus 0 by root of 1, which is 1. Same, this also goes to 1, same similar argument. In fact, I can probably say this computation can be made easier. For example, for the left hand side, we don't need to take n square plus 1, n square plus n and so on. We can simply take just n square by root of n power 6 plus n up to n square by root of n power 6 plus n. That is also lower bound, right? So we don't get this term. Anyway, it doesn't matter. Same goes for the right hand side. So is it clear? So both left hand side and right hand side has limit 1. So our sequence has limit 1. So again we use the sandwich theorem or squeeze theorem. So this you can always remember, like if you have a polynomial by polynomial, or it need not be a polynomial even, it can be a radical function like this, but it will be a square root of some polynomial or cube root or something. Then you look at the highest degree. So if both have the same degree, then the answer will always be the coefficient, the ratio of the coefficient of the numerator and the coefficient of the denominator. That's what happened in the previous question also. So you can quickly answer it. If you practice enough number of times, you will get the idea. So that's the thing. So if no doubt, then we will go to the next one. So here is another limit evaluation problem. So this is given this way. So let me write 1 divided by n to the n minus 1 summation k equal to 0 to n. So what is this term? Can you identify? N factorial by k factorial n minus k factorial.
NCK.
Yeah, so this is nothing but nck n to the power k by k plus 1. So what we have been asked is, so okay, so let's say this is n. So if beta is the limit of n, find the answer of log beta. So you don't forget about this. You have to read the question really well. So they have not asked the value of beta, value of log beta. Sometimes we miss that point and then we find the answer and then later we forgot about this, and yeah, our whole effort will be gone. So yeah, so our first objective is to find the limit of n. So how can one possibly find the limit? So we know some familiar to this, right? Summation nck something, some. So yeah, I did not hear properly. Yeah, so do you know any familiar summation nck n choose k, say n power k or something, right? We know the binomial expansion, right? nck, let's say x power k. What is this? Yeah, this is just the expansion of 1 plus x power n, right? So we need to see that directly, like when you see such a form, okay, this is somehow related to binomial expansion, but not exactly that. But you can do some manipulation and connect it with the one which you already know. So here there is an extra term like k plus 1 is coming in the denominator. That makes it problematic. We cannot directly say it is of this form. So so for example, if this k plus 1 was not there, this sum would have been just 1 plus n power n, right? So there is a k plus 1 here. So how can we manage that? What can we do to get that? Like, so yeah, if anyone has any idea, you can tell me. Otherwise, I'll move ahead. Okay. So one thing you can do is, okay. So what? Okay, let me say this possibly. What can I do to this expression to get something like x power k by k plus 1 or something like that?
Sir, if we do 1 plus k inverse.
1 plus
1 plus k whole inverse.
Just a second. 1 plus what? 1 plus?
1 plus k whole inverse.
Okay, so does it have a similar expansion? Like a finite sum of this form, binomial expansion. So yeah, so I mean, I don't just want to give you the answer, so I just want you to think. So
Integration.
sorry.
Integration.
Your voice was breaking. I could not hear
Integration.
properly. Yeah, exactly. Right. So when you integrate this expression, let's say this expression, if I so this one. Suppose if I integrate, what I get is summation right, x power k plus 1 by k plus 1. That's one way to get that form, right? So this is, one need to see this. One should have a view of this. How can one possibly get that from the expression which you already know? So, but here again, there is no k plus 1. But what one can do? Just multiply by n on numerator and denominator, right? So just put an n on the denominator. Just put an n on the numerator. Right? Now it is of that form. Is that clear? So you probably won't get the direct expression which you already know. One need to work on it and get the required answer. So the important thing is to have an idea of, okay, how we have to connect it with something which we know already, which is the binomial expansion, and then how can I arrive at such a sum from the binomial expansion. So when you integrate, you get it. So how can I write it in a proper way? So k equal to 0 to n choose k. So this number, what is it? It's nothing but integral 0 to n x power k dx, right? When you integrate x power k, you get x power k plus 1 by k plus 1. Just apply 0 to n. You get n power k plus 1 by k plus 1. Exactly that. Just let me know if you... so this is the idea behind it. Suppose if I am writing this without telling you the idea, then you don't understand. So that's why I let you think first. So now we can write the proof. But the idea that integration is the one need to do to achieve this. That is important thing. Writing the proof comes later. So now, because it's a finite sum, you can take the integral outside, right? So like 1 by n to the n integral 0 to n summation k equal to 0 to n choose k x power k dx. Now you know all the terms involved in the expression. 0 to n. So what is this? N summation n choose k x power k, which is exactly what we said. 1 plus x to the n. And this we know how to integrate, right? 1 plus x to the n, which is 1 plus x to the n plus 1 by n plus 1. So probably I will write on another page. So what we have is 1 by n to the n integral 0 to n 1 plus x to the n dx. So you see, initially the question was about some summation. Right now we are with an integral expression. So that's the thing. That's the beauty about this thing. We need to identify it as an integral form. That's the point. So now one can easily integrate this. What you get is 1 plus x power n plus 1 divided by n plus 1, which varies from 0 to n, which is now n plus 1 to the power n plus 1 divided by n plus 1 minus 1 by n plus 1. Now, you can clear one of the n plus 1 here and plus 1 here, right? So, what you get is n plus 1 to the n by n to the n minus 1 by. So, is it clear till now? So, essentially what we did is we wrote our original sequence, we simplified it and wrote it in the final form is this. Now, we just need to find the limit of this. You can ask questions if you have any. Now, how do one find limit of this first? Now, that's the next job. So, how do one find the limit of this? So, individually we can look at the first term, look at the second term, just find the limit and just take the difference. And so you can tell which, if you know one of them, limit of first one or second one. Yeah, if you are messaging, I probably won't be seeing now. So,
Sir, it will be E, right?
yes. So how?
We can take
how can
n
we say?
outside.
Yeah.
Then we will get n raised to n into 1 plus 1 by n raised to n. 1 plus 1 by n raised to n is E. Then
Okay,
n raised to n
good.
will be cancelled.
Okay, good. So just basically cancelling n raised to n. So you can write it in this form, right? This is a familiar limit, which is E minus what is the limit of this second one? 1 divided by n power n times n plus 1. So what is the denominator? It's going to infinity, right? 1 by n and way bigger than 1 by n. 1 by n power n plus 1. So it is 0, right? Is it clear? So the final answer is the beta, which is the limit of an is E. So we have been asked the log of the limit, which is 1. Okay. Tell me.
Experiments last how it is 0.
Yeah, so you know 1 by n goes to 0, goes towards 0.
Yes, sir.
So you can one way you can say it is okay. You can say the denominator is going towards infinity, right? The denominator term 1 by n power n, or you can write, yeah, or you can just if you want a proper argument, you can write as less than equal to 1 by n, right? So or something related to that, like 1 by n or 1.
Okay.
Yeah, so there are, because this is very smaller than 1 by n, right? So if in general, if the denominator sequence goes towards infinity, then the 1 divided by that sequence will be converging to 0. So that's the idea behind that. So limit goes towards E. So we have been asked about the log of the limits, which is 1. So the answer is 1. I hope it's clear. So it's about it's yeah. So fine. So if that is fine, let's move towards another question. Okay, this one, yeah, maybe we can discuss this one too. So what is given is that the x1, the first term is 0 or greater than 0, and define the xn plus 1 is xn plus 4. Then we have given the information that the limit of this is some number 1 by 24. Then find the value of x1. There are some options. So what does this thing tells you? Xn plus 1 plus. So it's like basically it's an arithmetic sequence, right? You have second term is 4 plus the previous term, the x1. The nth term is the 4 plus the previous term. So there is a common difference. 4 is the common difference, right? So is it clear? You have x1.
Yes,
Then
sir. So
yeah.
if you multiply and divide by 4, and then we can write xn plus 1 minus xn, then we substitute if we
Yes. So yeah, that will be better actually. So what she said is the following: because we know that xn plus 1 minus xn equal to 4, right? For each n. So that means you know x2 minus x1 is 4, x3 minus x2 is 4, and so on. So you want to find the limit of this, right? So multiply both numerator and denominator by 4. So what? 1 by 4 times 4 by x2 x3, 4 by x3 x4 plus 4 by xn plus 1 xn plus 2. Now why we did that? Because 4 is nothing but the difference of them, the what the terms involved in the denominator, right? So this is x3 minus x2 divided by x2 x3 plus this is x4 minus x3 divided by x3 x4 plus up to xn plus 2 minus xn plus 1 divided by xn plus 1 xn plus 2. Is it clear? Now why we wrote this way? Because now you can cancel the terms, right? Take one by one at a time. So x3 by x2 x3, that is 1 by x2 minus x2 by x2 x3, that is 1 by x3. Now if you look at the next term, what you get is 1 by x3 minus 1 by x4, and so on. It will go till the last one. So what you get is 1 by xn plus 1 minus 1 by xn plus 2, right? I hope it's clear. So now what happens is that the consecutive terms are getting cancelled. I am not writing the entire term, but if you write, it will be clear. So this is like a telescopic sum where the consecutive terms get cancelled. The next term will be 1 by x4 and so on. So only the remaining terms will be 1 divided by x2 minus 1 divided by xn plus 2. Is it clear, everyone?
Yes.
Yeah. So this number is given to be, sorry, not this number, limit of this number. So I just expanded the expression inside. So the limit of this thing. So maybe I will write in the next page. So what we are given is the limit of this expression 1 by 4 times 1 divided by x2 minus 1 divided by xn plus 2. This is given to be 1 divided by 24. That means you can take the limit, right? So that is, now this is a constant, right? This term 1 by x2, which is a constant term. Only the 1 by xn plus 2 is the thing which we need to look at. So 1 and 1 by 4, you can take it to the other side and make it 1 by 6. So the only thing remaining is 1 by x2 minus 1 divided by, then you can take limit, right? Limit xn or xn plus 2, both are the same. This is 1 divided by 6. I hope it's clear.
Yes,
Now what we have been asked is to find the value of x1. Okay. Now this is what we have. Now first of all, what is this limit? What is the limit of xn? Or maybe I will put the limit here, limit. I'm just taking limit inside, right? Limit n tend to infinity, 1 by xn plus 2. So
it will become 0.
Yeah, why it is that?
Because the n term is being written as downside. So 1 upon it will become infinity, which will become 0.
Yeah, so why xn goes to infinity?
In the x1 actually is greater than 0. So you can
Yeah.
actually say that xn is greater than 4 minus 4. So that's why.
Right. So basically, you can find in fact xn is a linear polynomial in n, right? Because as we said, it's an arithmetic progression. So you can find xn. In fact, the formula for xn will be some an plus b for some a and b, right? You can in fact find the exact formula, because so xn is actually some let me write. So x sorry, so it's exactly the same thing as he said. So x2 is 4 plus x1 and x3 is 4 plus x2, which is 4 plus x1, that is 2 times 4 plus x1. And similarly, your xn becomes, or xn plus 1 becomes n times 4, that is 4n, just inductively, plus x1. So yeah, exactly the same thing as we said. So this sequence goes towards infinity. Xn, the sequence xn, or xn plus 1 or xn plus 2, both. So therefore, so in fact, any arithmetic progression goes towards infinity, right? If your common difference is positive, then it goes towards infinity. If your common difference is negative, it goes the other way, minus infinity. So this goes towards infinity. Therefore, the entire sequence goes towards 0. Okay. Just for an explanation. So this, what you get is 1 by x2 minus 0 equal to 1 by 6. That means x2 equal to 6. But we want the value of x1. What is x1 then? Yeah, because x2 minus x1 is 4. So it has to be 2. So is it clear, everyone? Yeah. Then let's see another problem. I hope you can see it. So it's again a limit evaluation problem. So what is given? 8n times e to the power 1 by 2n minus 1. Then there is another term which is sine of 1 divided by 2n plus modulus of cos of 1 divided by 2n modulus. You want to find the limit of this. So you can see this as separate terms. So you are given some product of sequences. Now, maybe if you look at the right side term, what is the limit of this? What is the limit of sine 1 by 2n? So, where does this converge to and where does this converge to?
0 and 1.
Yeah, so what could be the reason? What sine for the sine 1 by 2n?
Sine 1 by 2n is rounded by 1 by 2n. So 1 by 2n converges to 0.
Okay. Yeah. And then what about cos? Yeah. In fact, yeah, that. But we cannot give the same argument for cos actually. Yeah, that's good. That argument is good, but in fact, we can do this, right? This sequence goes to 0, 1 by 2n, right? 1 by 2n goes to 0. Now, what we know?
Sine 0.
Yes, so why it should be sine 0, the limit of sine 1 by 2n. We know 1 by 2n goes to 0. Why sine of 1 by 2n goes to sine 0? So it's because sine function is continuous, right? So we cannot do this for any arbitrary function like 1 by 2n goes to 0. Then we cannot say that 1 by f of 1 by 2n goes to f of 0. We can have counter example. So the point is sine function is continuous at 0. So you have the sequential criterion for limits or sequential criterion for continuity, right? So if you have limit x tends to x naught, f of x equal to, let's say, some number L, that is if and only if for any sequence xn converging to x naught, f of xn converges to L. This is the property we are using. So we know that sin x is continuous at 0. So we know that limit x tends to 0, sin x is 0 or sin 0. Therefore, you apply this to get this result. So your xn is 1 by 2n, which converges to 0. So sin 1 by 2n converges to 0. So why I am elaborating that is that in general we cannot we cannot say for any arbitrary function just 1 by 2n converges to 0. That doesn't mean f of 1 by 2n converges to f of 0, but because the functions are continuous, that's why we are able to say this. So this converges to sin 0 plus the same goes for cos. Cosine function is continuous at 0. Also, there is a modulus there, which is modulus function is continuous, and the composition of modulus and cosine function is continuous. Therefore, the limit is modulus of cos of 0, which is 1. So entirely this sequence converges to 0 plus 1, which is 1. Maybe I am explaining too much, but just to make the concept clear. So in general, we cannot say this for any arbitrary function. We are basically using the continuity of the function involved. Okay, so that part is 1. Now we need to find the limit of this part.
Why is the modulus needed here?
Why is the modulus
needed here? Because it's always going to be positive.
No. Can you repeat?
Yes. So in the absolute value of cosine 1 over 2n, right?
Yeah.
As in approaches infinite, it's always going to be positive.
Yeah, modulus is always positive. Yes.
No. I'm saying the cosine 1 over 2n term, that is always going to be positive. So absolute value.
Okay. That is correct. Okay, you are right. Okay, that is maybe that is true. Yeah, in fact, in this particular case, you are right. you don't need modulus here because it's the argument inside the cosine function is always between 0 and pi by 2, where cosine is always positive. So yeah, you are right. In this case, it is not necessary. But yeah, in general, it will be nice to talk about this because you can take modulus of the limit. So
Yeah, of course.
yeah,
I'm talking about this as well.
yeah, yeah. So yeah, that's a good point. So the limit is 1 for the right hand side. So what about this term, this particular sequence? 8n times e to the 1 by 2n minus 1. So if you look at individually, this is like n is going towards infinity, and this is like e to the 0, right? E to the power with something going to 0, that is like 1 minus 1. So this kind of going to 0. So this is like 0 times infinity form. So which you probably know, this what we call as indeterminate form. You cannot determine from the expression given. So you need some kind of technique to overcome this, to find the limit. So what can one possibly do from this expression?
You can use the Maclaurin series.
Okay, so you're saying yeah, expansion of the exponential function. Okay,
Yeah.
that is fine, but we can do it in much better way.
L'Hopital rule we can use.
How do we apply that?
We can take the derivative at that point, like of numerator and denominator.
So where is the denominator? So it's already not in that form.
Okay.
How do we possibly write it? So there is no numerator and denominator as of now.
We can take the 8n down as 1 by 8n.
Yeah.
We can write n as 1 over n in denominator.
Okay, good. So let me write that. So you're saying that you can write this as e to the 1 by 2n minus 1 divided by 1 by 8n. That's okay. So now maybe I'll write in the next page, so because I am running out of space. So what you said is you write 8n times e to the 1 over 2n minus 1 as e to the 1 over 2n. By the way, somebody said use the expansion. That is also correct, but I will give an argument which doesn't use that. I mean, one will get the answer, but one need to still argue certain things. So this is one idea somebody said. So okay, this is numerator, denominator. Okay, now what one can do?
We can multiply and divide by 4, so that our denominator becomes 1 upon 2n, and then
Yeah.
we can take the limit.
Okay, so that means we can keep our 4 on the numerator itself. Then this is what you are saying, right? So
Yes.
so now what?
Now we can take the limit.
Yeah. So yeah, basically we want to take the limit of them. So limit. Okay. So yeah, what will be the limit?
4. Sir.
Yes. So how to get that? Like now you have an expression e to the 1 by 2n minus 1 by 1 by 2n. So what are you using?
Sir, there is a direct formula that we use to memorize e raised to power x minus 1 upon x, and when limit will tend towards infinity, it will go to 1.
Limit goes to infinity or 0?
Yeah. And the derivation follows from the Maclaurin expansion.
Okay, that's good. So this one, yeah.
So we can apply L'Hopital's rule and like do the derivative.
Right. You are right. You are right. We can apply, but that will be kind of a cheating, because if when you apply, you already assuming the existence of derivative and all. So I mean, you can always apply, and the answer you will always get the answer. But so So this is one thing. One he said we used to memorize one result, right? I think in class 12th or something or 11th. Limit. This is a standard limit we used to memorize. Limit x tends to 0 e to the x minus 1 by x equal to 1. One argument is you can apply L'Hospital and get the answer. But in fact, what is this? You can also memorize this as e to the x minus e to the 0 by x minus 0, which is basically, what is this? The derivative of the function e to the x at 0. That is e to the x itself at 0, that is 1. That's another way to see it. So it's actually the first limit, principal form of the limit. So you can use L'Hospital to get answer. To get answer, you can use multiple ways. So somebody also said use the Maclaurin series, power series, and just expand it out, and that way also one will get. So anyway, the point is the limit of you identify. This one as this limit, and now because this limit is 1, so the sequential criterion which we used above, which will give you, this is 4 times. Since this limit exists, that will be the same limit as this one, right? Because whenever you take any sequence converging to 0, you will get, let's say it is xn, e to the xn minus 1 by xn will converge to the limit 1. So in particular here the sequence xn we have taken is 1 by 2n. That's the argument. If you want to argue properly, but that you can basically compare with this, and the answer is 4 times 1, that is 4. So basically it is to identify the sequence in this way. Initially it was just in the indeterminate form. So then you divide this so that it makes it 0 by 0 form. Now you can do those things, whatever L'Hospital rule or identifying the non-limit or whatever things. Or here itself one can expand it out also. That is also possible. But sometimes we probably get into functions which we cannot expand. So we can only expand those functions which is expandable, which are power series expansion. So so we need to see all possible type of questions, right? So this is one possible argument. So here we didn't use any of those things like power series expansion or anything. We just use the standard limit property, and this is the answer. This is the limit of that term. So we had 2 terms. So this is 4 and this is 1. So altogether the answer is 4 into 1. This is 4. So I hope it's clear. If not, it just you can ask if there is any question. So let's see another question. This one. So we have given the sequence xn is minus 1 to the power n. So the question is, which of the following is false? That's very important. Which are false? So let's look at the first option. So there is an epsilon greater than 0 such that modulus of xn minus 1 is less than epsilon for all positive integers n. So let me write. What is this sequence, by the way? This is just minus 1.
Oscillating sequence.
Minus 1, 1, minus 1, 1, and so on. This is just that sequence. So all the odd terms will be minus 1. All the even terms will be 1. That's all. So this sequence only takes 2 values, minus 1 or 1. So having said that, let's look at the first option. Is this statement true? There is a number epsilon positive such that for all positive integers n, this quantity is less than epsilon. Can we get such an epsilon?
You can take epsilon to be 3 or 4 or something.
Yeah, so yeah, you are right. So what exactly is saying, like mod xn minus 1 less than epsilon means what? So essentially what this asks is that whether your sequence is bounded, right? Xn minus 1. So can you find a number such that xn minus 1 is bounded by some fixed, some fixed number. So what you do, like as he said, you take epsilon to be, let's say 3 or something. Because
Anything larger than 2 works actually.
yeah, exactly. You can take anything larger than 2. Take any epsilon. Let's say, for example, epsilon equal to 3. So what are the values of xn minus 1? Xn minus 1 has only possibilities are minus 2 and 0, right? So it always comes under less than 3, right? Minus 2 modulus is less than 3. Is it clear? So the question is whether there exists epsilon greater than 0 such that all the terms of xn minus 1 modulus is less than epsilon. Yeah, you can take epsilon to be 3, for example. So essentially what this question is whether the sequence is bounded or not, which is the case. So it is a true statement. So the option is wrong because we have been asked to find the false statements. If it's not clear, let's please ask. Otherwise, we will move towards the second one. So what is the second option? There is an epsilon greater than 0. There is a fixed number epsilon positive such that you take any positive number m. So for all positive number m, there is a positive number. So I will write it. For what its statement is saying that for all positive number m, there is a positive integer such that there is a positive integer n which is greater than m, for which you have modulus of x n minus 1 is greater than epsilon. So is it possible? Like, so there is a fixed epsilon. Epsilon is a fixed number. What they are saying is there is an epsilon which works for all m greater than 0. So for all m greater than 0, there is an n after which this is greater than epsilon. So is there such an epsilon? Can we, is the statement true? If it is so, then you provide me an epsilon which is greater than 0 such that this statement is true. That is, for all positive real numbers, there is a natural number bigger than that in which modulus of xn minus 1 is greater than epsilon. Yeah. So first of all, what are the possible values of this xn minus 1, which we already discussed, right? It is just minus 2 and 0, right? So modulus of xn minus 1 can only take 0 or 2. Is that clear? Whatever be n, modulus of xn minus 1 is always 0 or 2. So what can I choose and can I find an epsilon such that this happens from some positive epsilon? Yes, right? Like I can take any epsilon greater than 0, right? Whatever epsilon I take, then whatever m is given to me, let's say, I can always find a what do you say, like I will take epsilon to be, let's say, let me take epsilon to be, for example, 1. Now whatever m greater than 0 is given to you, I will choose an n greater than m, which is let's say odd, which I can do, right? Then mod xn minus 1 is what? In the odd position, it is minus 1, that is 2, which is greater than epsilon. Epsilon is 1, which I have started with. So probably this can create some confusion because this is a logical statement. So one need to sit and
Sir,
understand.
one doubt.
Yeah.
Option 1. Suppose we take epsilon equal to half.
Okay.
The modulus of xn minus 1 is either 1 or 0 we get.
You are talking about option 1, right? Yeah,
yes.
Okay.
Epsilon equal to 1 by 2.
Okay.
So we fix epsilon equal to 1 by 2. The modulus of xn minus 1 is either 1 or either 1 or some. Wait a minute.
Okay. Yeah, take your time.
Okay. 2 minus. Okay. Sorry, sir.
Yeah, fine.
Okay. Suppose it is not valid now. Suppose we are modulus of xn minus 1 less than epsilon. Suppose we are fixing epsilon equal to 1 by 2.
Okay.
Modulus of xn minus 1 is either 1 or 1 less than 1 by 2. It is not possible now.
Yeah. Yeah. So because that's what we said. Look, there are modulus of xn minus 1 is always 0 or 2.
Yes, sir.
So you cannot take epsilon to be half because it will violate when we are in the odd position. N is odd, then xn minus 1, modulus of xn minus 1 is always 2.
Yes, sir.
So it cannot be less than half.
Yes, sir.
So that's why we are always taking, that's why we said we can take epsilon to be any number greater than 2.
Oh.
That was the idea we used.
Okay, sir. Okay. Thank you.
Yeah. So coming back to this question. So anyone has any doubt on what I said? So one needs to understand the statement. That's the main thing. If you understand, then it's actually straightforward. So what I said is this statement is true actually. Like for example, take epsilon to be 1. There is an epsilon which I am saying. Let's say epsilon to be 1. Such that for all positive real numbers m greater than 0, what I will do? There exists a positive integer. Yes, you can take n to be odd. So any positive number given to you, take a number bigger than that which is odd, right? Then what is mod xn minus 1? That is 2, which is greater than epsilon, which I have taken. So that statement is always true. That means this is not a correct option because we want false options. Is that clear? Yeah. So the thing is, sometimes we can get confused because it's a logical statement. There is epsilon, m, n is there. So we need to sit down and understand what the statement means first of all.
Sir, is it not like for all capital N greater than capital M? It's just for that particular.
No, what it says is for any positive number given, there is a number, not for all. For any positive real number given to you.
Okay, sir.
There is. Can you find an element, a number, positive number greater than that, such that this happens? That's all.
Okay, suppose like if before that n greater than m, if for all n greater than m is there, This is not.
Yeah, then we want, because
Yeah,
if you take n to be even, that will be 0. That expression
Yeah,
is 0. Then you cannot. So
Yeah, okay, sir. Thank you.
yeah, if that is clear to everybody, we can move towards the third option. Okay. So what is the third option? For all epsilon greater than 0 and for all m greater than 0. Okay. So epsilon greater than 0 and m greater than 0 is arbitrarily chosen. Then there exists a positive integer n which is greater than m and mod xn minus 1 is less than epsilon. Is it clear? What it says, for all epsilon greater than 0 and an arbitrary chosen real number m, positive real number. What it says is there is always a positive integer n which is greater than that number, such that modulus of that xn minus 1 is less than epsilon. Is it true? But epsilon is arbitrary. It is always true, right? Because you can always take n to be even. Is that so? You can always find an even number bigger than m. So when n is even, as we said, xn is always 1. So xn minus 1 is 0. So in the eventh position, this sequence is always 1. Therefore, xn minus 1 sequence is always 0. And 0 is always less than epsilon, whatever epsilon you have started with. Isn't it? So for all epsilon greater than 0 and for all m greater than 0, yes, you can always find a positive integer. Take any even integer greater than m. Right? Take any even integer.
Sir, I have one doubt.
Yeah.
Sir, this statement, like m greater than 0, there exists a positive integer n such that n greater than m. So this means that n is a positive number.
Yeah, m can be taken to be any positive number.
Sir,
Any real number.
m is totally unnecessary, I think, because
Yeah. You can take it to be any number.
And sir, if I and given that for all epsilon greater than 0, suppose I take epsilon is equal to 1 and I take this value mod of xn minus 1 is equal to 2, then 2 less than 1. Then it will be.
Which one you are talking about? The C option?
Yes, sir.
The question is not for all n, whether there is an n such that mod xn minus 1 is less than epsilon. You said, if you take xn to be minus 1, that is in the case when n is odd, right? In that case, it is 2. But I can also take n to be even. The index n to be even. So in the even position, we know that this thing is 0. So did you get the point? So you are right, this becomes 2 also, but we only want existence of some integer n for which this happens. I am saying take n to be any even integer.
Yes, sir. I get it.
Yeah. So point is, this statement is true. Yeah, so basically this is a logical, question from logic also, because one needs to really sit down and understand what exactly it is said. That can create confusion at sometimes. So so because these 3 options are wrong, so this has to be the correct option. That means this should be the false statement. Let's see what it is. So what it says, for all epsilon greater than 0 and for all m greater than 0, there is a positive integer n such that modulus of xn minus 1 is greater than epsilon. Can we say that? The same thing, but they just replaced it less than epsilon by greater than epsilon. So is it true for all epsilon? See, again, look at the values of xn minus 1. This is either 0 or 2.
So what if at 2 my epsilon is 4? It won't be true, right?
When your epsilon is?
4.
Yeah, if your epsilon is 4, then it is always true. But it should be, if we are saying the statement is right, it should be true for all epsilon greater than 0 and m greater than 0. So you said 4, yeah, it is right. But you can take epsilon, smaller values of epsilon. For that also, this statement should be true. So for example, I am taking, let's say, epsilon equal to 1. Okay. Is the statement true? That is, there always exists an integer such that mod xn minus 1 is greater than epsilon. Oh, okay. So you said the epsilon to be 4, right? Something, yeah, some bigger number. Yeah, that works actually. Sorry, I was little confused. Yeah, 4 or any bigger number. So what, as we said above, like we can take epsilon to be any number bigger than, let's say, 1. Yeah, so probably so okay, 4 or something bigger might work. Maybe epsilon equal to 1 does not work. Yeah, 4 or if you take so you are actually you are right. So epsilon equal to 4 or any bigger number, if you take, this number cannot be bigger than that epsilon, right? Anything bigger than 2 should work. Is that clear? Because this number can never be bigger than 2, because the only possibilities is 0 or 2. So if your epsilon which you are taking is greater than 2, this inequality won't follow, right? So therefore the statement is wrong. You can take, as she said, epsilon equal to 4, or in fact any number greater than 2, it will work. So the statement is false. So this is the correct option. Is it clear? Okay. So yeah, so what can we do? So shall we continue one more, or okay, I have some more questions. Maybe one more question we will discuss and then we'll stop. So so which of the following statements are true? It's about sequence. So what it says, there exists a monotone sequence that does not converge, but it has a convergent subsequence. It's a monotone sequence, but does not converge. Can it have a convergent subsequence?
No.
Yeah, so this is false. Can you say the reasoning in say a few words? What could be the reason? So monotone sequence means it's either monotonically increasing or decreasing, right? So sequence is monotone, let's say increasing. Yeah. So, and it's also saying it does not converge.
So if we take 1 by n, which is a divergent sequence, it does not converge. But if we take 1 by 2n, which is a subsequence, but it is not convergent subsequence.
You what is your sequence? 1 by n.
Yes, sir.
But that converges, right?
Sorry, sir.
So you basically want to
N. I meant to say n.
Okay. So
As n is a monotonic sequence which does
Yeah.
not converge. But
Yeah.
if we take 2n, 3n in that way subsequence, which is not having a convergent subsequence.
but you are talking about a particular sequence, right? The question is whether there exists a monotone sequence having that property. But you said, okay, xn equal to n does not have that property. But what if some other sequence has? So if you want to say this is wrong, you want to say that this is not possible at all for any such sequence.
Sir, NB increasing sequence and subsequence is constant, any constant sequence, then it will be convergent. But N is not convergent sequence.
Oh, so you are saying the statement is true. We can find a sequence which is
Sir, if we take a sequence N, 1, 2, 3, 4,
Oh,
like that.
okay.
So it is a monotone sequence.
Okay, does not converge.
But if we take its subsequence like 2, 2, 2, so this is convergent subsequence.
But 2, 2, 2, which you said is not a subsequence, right? We cannot repeat that again and again because all the terms are different.
Sir, here the sequence may not be bounded because it is not convergent, no?
Exactly.
So if the sequence itself is not bounded,
Yeah.
so its subsequent can also not be bounded, right? So
That
not
is
bounded
because
implies not convergent.
Yeah, you are right. You are using monotone property also, right? At the same time.
Yes, sir.
Yeah. So what you said is, so we have something called monotone convergence theorem, right? Monotone convergence theorem, which says, so for I will write for increasing, the same goes for decreasing. So if xn is increasing and xn bounded above, then xn is convergent. In fact, xn, what is the limit xn? It is the supremum.
Supremum.
Right. So this is the monotone convergence theorem for the increasing case. For decreasing case, it will converge to the infimum. So what we are looking for is a sequence, monotone sequence that does not converge. That means what? If it is increasing, it should not be bounded above, right? So we are looking at a monotone sequence xn. So like x1 bigger than x2 less than xn plus 1, which is not bounded above. The same argument can be given for bounded below also. So let's say we take an increasing sequence which is not bounded above. This means what? So the xn does not converge, so that means xn keeps on increasing, right? So you can actually show that xn as a sequence, it diverges to infinity. as n tends to infinity, just by definition. Because of the monotone property and the fact that it is not bounded above, xn becomes as large as possible as you go on. So xn goes towards infinity. Now xn is a sequence, has this property. You take any subsequence, xn k something, you can show that this also goes towards infinity. It's a subsequence of something going to infinity. So if you have a sequence convergent, any subsequence is convergent, right? Similar to that, if a sequence converges to or diverges to infinity, any subsequence diverges to infinity. So if you have a monotone sequence that does not converge, any subsequence also does not converge. So this is not true. We cannot have a convergent subsequence. The statement is not true. So this is one possible argument. Somebody also said by boundedness, that is also correct. So for a monotone sequence that is not converging, that is not bounded above, the subsequence also cannot be bounded above. We are just using the monotonous property. So this statement is not true. I hope it's clear. So what about the second one? So there exists a sequence that has a bounded subsequence but does not have any convergent subsequence. So your sequence has a bounded subsequence already. So what can we say? So you can use Bolzano-Weierstrass theorem, right? Any bounded sequence has a convergent subsequence. So your original sequence xn has a bounded subsequence. That bounded subsequence has a convergent subsequence. So that subsequence becomes a subsequence of the original sequence, right? So this statement is also wrong. So we are basically using the Bolzano-Weierstrass theorem. Is it clear? Yeah. So what about the third option? So what it says, there is a sequence xn such that given any integer m, positive integer m, xn has a subsequence converging to that number. So that means the question is whether there is such a sequence exists, or in other words, can you find a sequence xn such that it has a convergent subsequence which converges to 1, also 2, 3, 4, and so on. Does such a sequence exist? It should have a subsequence converging to 1. It should have a subsequence converging to 2. It should have a subsequence converging to 3, and so on. Whether such a sequence exists or not. Can we construct such a sequence, or can we argue that okay, such sequence cannot exist? Yeah, if you have any idea, you can tell. Even if it is wrong, we can discuss that, because we can discuss why it is wrong. So how can we do that, like for each integer? So first of all, yeah, so how do so you have to visualize this, right? So there is a sequence where
Sir,
yeah.
can I take a sequence 1, 1, 2, 1, 2, 3,
Okay.
1, 2, 3, 4?
Yeah.
Like that?
Like that, yes, you are right. So yeah, this is one possible example which you can take. So just first term is 1, then 1, 2, then 1, 2, 3, then 1, 2, 3, 4, and so on. This is a well-defined sequence, right? So it has each of the numbers is repeating infinitely many times, right? So 1, 1, this one, and so on. This is a subsequence. Then 2 is repeating infinitely many times. 3 is repeating. We are choosing the sequence in that way. So you have a constant subsequence, in fact. Subsequence which contains constants for each integer m. So that is one good example. So this is actually a true statement. In fact, yeah, this is one way to consider. In fact, actually, you can construct a sequence such that any real number is in fact, there is a subsequence which converges to any real number, not just positive integer, any real number. How can we do that? So this, I'm talking about something stronger than this. So here we have only asked for any positive integer. So you know the rational numbers, right? So rational numbers are dense in real numbers. So you just take a sequence of rational numbers, Rn. Take an enumeration of rational numbers. We know it is a countable set. So we can take an enumeration of rational numbers. So this sequence always has a subsequence which converges to any of the real numbers. So in particular, integers also belongs there. So in that way, one can argue. Another example which I can possibly give is, let's say, let's define one sequence xn to be number of prime factors of n. Just to give some more good examples. We already answered it is yes, true, right? Define xn to be number of prime factors of n. So for example, first term I am defining to be 1, then x2 onwards I define in the following way. Xn is number of prime factors of n. So x2 is 2. So in fact, what you get is, maybe I will write here, what is xp, any prime? There is only one factor, right? xp is 1 for all prime p. Right? For a prime, there is only one prime factor. So in the primeth position, the sequence is always 1. So we know that number of primes is infinite, right? So there are infinitely many ones in that sequence. So 1 is repeated infinitely many times. So there is a subsequence which converges to 1. Similarly, you can get for 2, right? Take 2 different primes, distinct primes. Look at those numbers: p1, p2, p1, p2, p1 square, p2, all those possible. There are infinitely many. So right. So for each number n, each number m, we can find a number which has m many prime factors. And there are infinitely many of them. So yeah, I am giving some more examples just to give there are more. So this one is actually good. So
Sir, can you please repeat again this prime example?
Yeah, sure. So what I said is xn. Okay, x1 I am defining to be 1. Xn is for n greater than or equal to 2. I will define xn to be number of prime factors of n. How many prime factors does n has? So we know that any number has a prime decomposition, right? That's a well-defined number, right? Fundamental theorem of arithmetic. So you have a fixed number of prime factors for a given number. So this is a well-defined sequence. Now, what I'm saying is, first of all, xp equal to 1, right? For all prime p. That means on the primeth position, that is 2, second position, third position, 5th position, 7th position, 11th position, and so on. And we know number of primes are infinite. So in each of those positions, the value is 1 sequence. So there is a subsequence which consists of only 1. That means it converges to 1. So you have a subsequence converges to 1. Now, can you find infinitely many such numbers which has 2 as the value? Sequence takes 2. That means, can you find numbers like has just 2 prime factors? Can you find infinitely many numbers? You can, right? So you take numbers of the, let's say 2, you fix 2 primes. So let's say 2 and 3. 2 into 3, 2 square into 3, 2 into 3 square, whichever is the order, increasing order. Like you can go like 2 power m into 3 power n, right? In general, for all these positions, x xn is, if n is any of these numbers, okay, let me write xn is 2, right? Just 2 prime factors. These are the numbers which have 2 prime factors. I just take 2 into 2 and 3 and so on. Did you get my point? Like these are there are infinitely many such numbers which has the value at that xn is 2. Same way you can do for 3, 4 and so on. That's what I mean. Is that clear now?
Yes, sir.
Yeah. So the option C is correct. Now what about option D? So there exists a sequence xn such that modulus of xn plus 1 minus xn converges to 0, but the sequence xn does not converge. So I'll write here. You want a sequence, this should converge to 0, but xn does not converge. Can you find a sequence? That's the question.
Sir?
Yeah.
Sir, can I take summation 1 by n?
Yeah, so you mean xn is this one?
Yes,
right?
sir. Yes, sir.
Yeah. So can you explain why this belongs to this category? This
So because xn plus 1 minus xn will give 1 by n plus 1.
Exactly.
So that will converge to 0.
Yes.
And this, I know, summation of 1 by n is not converged to any number.
Exactly. So series 1 by n diverges. So xn does not converge, but xn plus 1 minus xn converges to 0. So is it clear to everyone? So this is one such sequence. Yeah, you can also take xn equal to root 10 or something. That also works. Yeah, but this is a good example. So root 10 does not converge, right? But xn plus 1 minus root 10 plus 1 minus root 10, right? How can you do that? Like you can multiply by root 10 plus 1 plus n root 10 on the numerator and denominator, you get this. This converges to 0. So this also is another example. Yeah, so the point is there exist such sequences. So it is true. Is that clear?
For option 3,
okay,
someone gives a sequence 1, 1, 2, 1, 2, 3, 1, 2, 3, 4.
Yeah.
Actually, that my doubt is suppose I found out subsequence A to n. But the second position is 1, fourth position is 1, but sixth position is not it's not 1. That no, it is not a subsequence. It is not in order. 1. It is something will becomes. No?
Yeah, but that is for the particular sequence which you said. But
yes.
The question is whether there are subsequences converging to a number, converging to each number.
Okay.
So the subsequence which you took is even position, right?
I took even position. Yes.
Yeah, that need not converge. What we are saying is whether
We
there
can
are
find any
some,
subsequence converges to some that one m that one. Yeah, that itself. I am asking. That's it.
Yeah, that's all we are saying. We can find subsequences which converging to 1, 2, 3, and so on. But if you randomly say a subsequence, that need not converge.
Oh, okay.
Yeah. Yeah. So, any other doubts? If not, I will stop. Yeah, you can also ask.
Okay. Yeah. Okay. Thank you, Anand. Yeah.
Yes, sir. Yeah.
So let's keep the video on. We'll move for a feedback session. Okay, thank you, Anand, for this nice session. I'm sure that our participants really enjoyed the session. Now, dear participants, it is your time to share your feedback, or if you have any doubt regarding MSc or PhD preparations, you can share it with Dr. Anand. So feel free to share your comments. You can turn your video on and your mic on, and you can express your feedback.
Hello.
Yeah. Hello.
Hello, sir. I'm Archana. I have completed my BSc at 𝐋𝐞𝐚𝐫𝐧𝐌𝐚 College. I have attempted JAM and cleared it last year.
Oh.
But your class was really refreshing because after the exam, I haven't touched the book. So it's sort of a revision, sort of a recap this was. So I really enjoyed the session. You explained everything in detail, like including each option rather than just taking the correct one and explaining in only that one in detail. So I really enjoyed your class. Looking for further classes. If you could take net related sessions too, it would be really good, sir.
Sure.
Thank
Sure,
you, sir.
sure.
Thank you, Vinod, sir, for organizing the session.
Okay, thank you, Archana. Yes, others?
So it's my very first time seeing a class of JAM, and I'm very glad that it was from you. And the main thing is that I like the most you explain each option. I thought you will only explain the correct one, which of these are true. You only say the correct one, but you explain all the ones which cleared my almost doubts. I was rather confused with the logical statements of usually for all the Rexes. It creates so much confusion with me, but you explain each step clearly. It's gave me so much motivation and inspiration, sir. Thank you, sir. And
Thank you so much. Thank you so much.
And thank you, sir, Vinod, sir, for organizing this thing. It's a very good initiative, and I'm pretty sad because I only knew this in this moment.
Okay, thank you, Sonu. Yeah, others? Yeah.
Am I audible?
Yeah, yes, Sajid.
Yeah, yes, sir. So thank you so much for spending your valuable time at this, most probably a weekend, sir. And all your, whatever the concepts you've explained was so clear actually. And this is I have started to study real from the past week. So this is actually a first lecture so that I could go with this point of view and I could solve a lot of questions. And thank you so much, Vinod, sir, for organizing like this. And you explained all the options, right? So that we could check whether some other options might be working or not, so that we could get a correct answer and correct point. Thank you, sir. Thank you so much.
Thank you.
Okay, thank you, Ajay. The members, feel free to share your feedback with video and audio. Yeah, some of you have shared your feedback in the chat box. So feel free to share your feedback with video and audio, and also it will be good if you introduce yourself, like where are you studying and all. It will be good. Yeah. Any others? if you would like to ask anything regarding PhD or IIT, that also you can do now. Yeah, Anand, let me ask one thing. Yeah, some of our members, even the participants in this session, are now planning to go for MSc in IIT. And most of them are from, they have did their bachelor's from a usual college. So definitely there will be some kind of issues will be there. Some struggle is will be there. So what is your advice to those students who are now moving to IIT for their MSc?
Yeah, I can say a few things like, yeah, I also did my, as you introduced, did my BSc from a normal college in Kerala. So, like, one thing about this kind of entrance examination is that you will have to, so in the college you will study certain things, theorems and all those things, and then you won't be exposed with solving these kind of problems. The kind of problems is asked in this kind of national level examinations like JAM or other exams. So one reason we are not able to solve such problems is that we are not used to solving such level problems. What I would say is, if you are getting used to these things, if you solve more and more problems, that's what happened in my case. You practice more and more problems, you get used to these things and techniques and all those things, so that it will always be in your brain. Next time you see the same kind of things, that approach will come to your mind naturally. Like sometimes maybe in the session you may have seen something new to you, but later next time you see something same, you will be able to solve it because you have seen it before. So the idea is to getting used to these things. Unfortunately, from what we are learning in colleges, we are not doing such things. And in fact we don't need to do also, because so we probably need to study separately. So learn the concepts well, that is always there, and then find sufficiently many time in your you do your homework well, practice problems more and more, and you will get used to these things. That's all. That's what happened in my case. In fact, the thing about these exams is that you have a time bound also. So even if you know how to solve it, you should solve it in given time. So by practicing more and more problems, you are also reducing the number of minutes or seconds you take to solve a problem. So that also gets improved, and that is the key to get good marks, I would say. But yeah, overall, that's the idea behind, or I would say, for this clearing these exams, entrance examination. Yeah, you have to learn each concepts really well from textbooks and whatever sources you use. Then solve as many as you can. That's the key, basically. Okay.
Okay, another one more thing. So, as you have studied your BSc in a regular college and then gone for MSc in an IIT, so could you say something about the difference of teaching learning process?
Yeah, sure. Like, yeah, the atmosphere is completely different when you come to IIT, because you get, first of all, rather than from academics, you have a lot of facilities here, there. You can do a lot of extracurricular activities and sports or other arts and everything. And coming to academics, like the faculties there are people who are doing active research. So that gives you motivation to go further towards the subject after MSc. There are people who are constantly working in different areas in mathematics. So you will get to know what kind of research are happening in mathematics, and that way you will get introduced to many different areas or topics in maths. So yeah, that is a different thing in overall in itself, that you will be working with different faculties and you can do projects or seminars or with them. That is completely different from what we have from in our usual colleges. Yeah, so yeah, there's a lot of exposure when you come to institute like IITs. There are more other institutes like CMI, ISI. You should aim for all the institute, I would say. So yeah, that is, if I can say. Yeah.
Okay. Okay. Thank you, Anand.
Thank you.
Any other would like to share any feedback or ask any question? Otherwise, we will wind up the session here. Yeah, once again, thanks to Anand for being with Math Aspirants, and hope that you will engage more sessions this time, and wish you all success in your academic career.
Yes, sir. Thank you. Thank you so much. Yeah,
So
sure we will.
Yeah.
Sure
So
we will meet again.
Yeah. Dear participants, please do participate actively in the forthcoming sessions as well. Wishing you all the very best in your preparations. Okay, thank you. Let us wind up here. Bye.
Bye.